Good evening, everyone. Welcome to another session of the Network Seminar series hosted by the Network series. And it's my pleasure to introduce today's speaker, Balaji Ganesan, generation for query and data lakehouse. Balaji Ganesan is a senior research engineer at IBM Media Research Lab. He's part of the data and AI department under IBM Research BI. He currently works on large language models, knowledge graphs, LLM agents, and their application with semantic automation, like text-to-SQL and text-to-GraphQL. He has previously worked on Petition Drafting and prediction using GraphQL networks, especially focusing on experiments. Balaji was previously at Yahoo and a number of startups in search and computational advertising. He graduated with a bachelor's degree in computer science engineering from the University of Madras in 2003 and a master's degree in computer science from the University of Arizona in 2003. Over to you.
All right, thank you. Okay, so yeah, I mean, I'm not really sure whether you have had a talk, more of a applied research talk before, but it's not fully applied research. Like later on, like this kind of the talk is divided into two portions. Initially, I will talk more sort of an applied work, and later on we will see some papers which we are working on in reasoning. That is more like we could say that it's more research. All right. So GraphQL, I mean, actually like the topic is GraphQL generation or schema generation for querying a lakehouse. So before we even get into this, like data lakehouse is sort of a new, relatively new, like it's been around for a few years now, new way of enterprises to store and query data. I mean, there have been things like databases have been around for a while, and there have been like few sort of like updates to this. Like databases became data warehouses. Then came what are called as data lakes. After that, there has been a sort of a flux in the enterprises. There is an ideology called data mesh, and there are people who swear by data lake. And sort of like data lakehouse is sort of a compromise between these two ideas. So in general, what this, I mean, without getting into the all the details of data mesh and data lake and data lakehouse, what this means is you can think of this as a pretty large, like say, database where the store in which the actual data is present is immaterial. So this is more like a framework. You can kind of use any kind of store to store, I mean, kind of keep all your enterprise data. And data lakehouse enables querying for different kinds of people. It could be end users, it could be, say, data stewards, or data analysts, or data scientists. All kinds of persona can query the data here. So that's the data lakehouse. If like if anyone is not familiar with data lakehouse in general. Okay, so GraphQL is again, I have a slide, next slide on what is GraphQL and why we should care about it. But GraphQL is again like a querying language similar to like say SQL, or you can think of this as a equivalent to REST APIs. So what we are going to talk about in this next 45 minutes is how can we make use of GraphQL to query the lakehouse, right? So it's not humans querying. Instead, like humans, if at all involved, they will make a natural language request, which will be converted into a GraphQL query, and the GraphQL query will be like kind of run on a GraphQL schema. So we will get more into the details, but this is the kind of a motivation. So what is GraphQL and why we should care instead of the two other things that I mentioned, SQL and REST APIs? In general, like SQL can do a lot of things GraphQL also does, except that SQLs are meant for querying databases. Whereas GraphQL kind of straddles both databases as well as REST APIs or APIs in general. So if there is a query language which can query both databases as well as APIs, then it kind of opens up all kinds of possibilities in the what is called as front end, but usually what is called as middleware. So imagine that you have to fetch some data and then you have to do some action. For example, like you want to take the data from say your DB2 or a SQL server and then write a report or write a document or like write it in some GitHub issue. So you would want to talk to GitHub using APIs and you would want to talk to the database just like you will do using SQL. So that's the first advantage. So that's like why even GraphQL exists. GraphQL was introduced by Facebook, now Meta, in 2014, and then they kind of open sourced it. Now GraphQL is managed by its own GraphQL Foundation. Now the contrast is the main advantage, like people can still use SQL to do a lot of querying. The main advantage compared to SQL is what is called as the overflow or like underfetching or overfetching problem. So what I mean by that is usually like if you have a table and you query like this here, in this case like you have a lot of columns in a table and there are multiple tables being queried here. Now I mean like if you know all the exact columns that you are interested in, maybe you will fetch the exact query or exact data that you want. But imagine if this is a language model which is generating this query, then maybe it would probably like be more liberal and then fetch lot more data, and then like you can call this as like overfetching of data. And also sometimes like because these are like say tables, there might be lots of IDs or like say simply like some timestamps, lot of columns which are present in a table which we may not care about once we have fetched this data. These kind of problems don't exist in GraphQL because in GraphQL you think more like a object-oriented programming language. Like say you think in terms of entities, their like kind of features or characteristics, and then like say their relationships. So this kind of opens up like say more flexibility in querying, and it also like kind of I mean like if someone is asking for I want a list of people, you probably are not interested in their timestamp. So you can be like more precise in fetching the data. This is like a lot of advantages in like say an app which gets data from say some backend. You don't want to get too much data that you have to handle in the front end. So okay, correct, correct. Right. So like just like we call say actually what happens in GraphQL is GraphQL itself is not a store. GraphQL fetches the data from some backend, and this backend can be any store like a MySQL or Postgres, or it can also be a REST API. You simply say that I want to fetch data from say this API. All right. So REST APIs are like say, I mean, I guess like the de facto standard for serving data and services, where a programmer or like a data model or an ontologist creates a bunch of endpoints, which we assume that the users of this service would want. So I created, maybe I have some data. I want to expose this data to people, application developers, and then I create a bunch of say like endpoints and let them query the data whenever they want. Mm-hmm. So like say in this case, this is sorry. So this is an example of an endpoint. So imagine that employees is a table or departments is a table, and this could be present in some say like say employee master or say an organization database. Correct. Correct. So, I mean, this, I mean, if you remember, like there was a story how the like kind of consuming services through APIs became quite popular. Amazon probably started it, and then it became the industry standard. So, basically, even within an organization, people don't want to like give access to a database and say that you query the database if you want the data. Instead, the push is towards each team or each like say module to expose their capabilities in the form of a REST API, which other teams can query either through programmatically or if they want using like say something called a Swagger API, which kind of you can even manually go through and give the credentials and get the data. So this idea of consuming services through APIs sort of has been established, and REST APIs like sort of have been the de facto standard. And GraphQL has been like kind of creeping into this market a little. I mean, probably like it's 1/5 of the market now, where a lot of application developers want to use GraphQL because of like some of the advantages that we just talked about. And for the most part, people might still be consuming REST API through GraphQL. Correct. Yeah, that's a good. Yeah, that's a good way to put it. Yes. All right. Cool. So, yeah, I mean, I guess like I hope this discussion was useful in kind of understanding why GraphQL exists. So, I think like 2-3 points came out. One is that GraphQL is used to query APIs, and APIs themselves have been usually like this under the REST APIs. Now, people have been moving towards slightly more flexible ones. We will see examples of GraphQL APIs. And second, GraphQL can be used to query not just the APIs, but also tables like this. So, I mean, besides the advantages mentioned here, these are like sort of the like kind of more layman terms to understand GraphQL. All right, so now we will kind of go very quickly into the nitty-gritty of things. So, like when we started working in this space, our goal was to sort of generate GraphQL queries. I will give examples of GraphQL queries momentarily. We want to generate these using LLMs. Like pretty much like nobody wants to write these GraphQL queries manually, because these are supposed to be like kind of course, the developers might want to improve it, but nobody wants to start writing GraphQL from scratch. So even SQL for that matter, like, do we really want to write queries all the time? Like, unless like you created the data model, you may not want to write SQLs anymore. So that's the motivation. Like, so can we generate GraphQL through LLMs, and predominantly for the purpose of data retrieval? So of course, the REST APIs also are for data retrieval, except that in this case, we are slightly more concerned about data lakehouse or databases in general. So it's not just the REST APIs, but we also have a flavor of databases. So that was our motivation. So we kind of recently gave a demo in Ichkai on this. The rest of the talk will kind of build on this. Like, so this was the motivation. We kind of set out what we want to do in this demo, and then like we have been implementing this like for the past year. All right. So this was the demo. So what we are saying here is we can query both databases as well as APIs, or a combination of both. So in this case, we will come to schema in a bit. Let's assume that the schema is already present. The schema is similar to a SQL table. So you have like the table name and then all the columns here, which are represented more like a like say an ontology or a object-oriented concept fashion. So you have like type, which is people, probably the table name, and all these are the columns. One significant change from databases is here you also need to provide how this data is going to be accessed. So it actually turned out that this is not in fact a table. This is in fact simply getting the data from this REST endpoint. So at this point, like when we are querying it, we don't even care whether the data is stored in a database or it's stored in some other REST API. Okay. So this is the like sort of what is given to us. Now on the right hand side is what we want to do. So we want to be able to run queries on this, but we are lazy. We don't want to write the GraphQL ourselves. We just want to give this in natural language. So this data set is like about some bodybuilding. So don't worry too much about the actual semantics here. It just says just give me snatch, which is a type of lift of all the bodybuilders and the average snatch. So this is it's just a toy data set. But you can imagine this in like say an enterprise. You can say that give me the say average salary of all the employees in this department or something. And we want to generate this using some language model. So Granite is an IBM language model. It has multiple versions. We are using the code models. So an equivalent to this would be the Code Llama, or I mean, of course, much larger models like Sonnet or ChatGPT, all those kind of things. But in general, in this case, we are using IBM's Granite models. So you might be familiar how these queries are written, like how these prompts are constructed. Usually there is an instruction. Optionally, there could be few short examples and then the actual question you want to ask. These are the three major components. Of course, in this case, we are not assuming any fancy prompting just yet. We are simply saying we will just give vanilla, like say llama style or a plain like a few short prompt. So I mean, so in this case, like usually the models may not like, so the models like that are trained, they are usually trained to implement an instruction. So they are trained to like they are given lots of instructions. So in that sense, the models are not trained on one task. They are generally trained to implement whatever instruction they are given. And because they are decent enough to like understand what is the instruction, we could do few things. One, we can simply give the instruction, the task as an instruction, but that may not be enough. So in this case, like typically, like even for us to understand, it's better to give some examples. So in this case, we give few examples. Like this is the natural language utterance. This is the query. See some 3-4 examples of this. Now I want you to do the same with the new query. Yeah, we pretty much dumped this. It says training example 0, and then we gave the schema, and then the okay. So in this case, this is not a fine-tuned model. So it's not fine-tuned on this task, although eventually we can. So these models are generally trained on, like say that just like any other model to predict the next token. On top of that, they have been further instruction trained where they are given like a set of about 18 or tasks on which like they have been trained, so that given some instruction, even without having seen a lot of examples of that, they can do that particular task. So this instruction tuning like is like sort of a fine tuning, except that we are focusing more on the model being able to follow the instructions. Yeah, it's yeah, actually like I mean this is I mean one of the recent like say like controversies around is how much of the context, like say instruction, few short examples and query, all of this we call as the context. Now how much of the context does the model understand? That's actually a somewhat of a open problem. But we, for the purpose of this, we know that transformers can predict the next token. So that much we know, that if we give a sentence, we leave the model some question mark or just colon, then it can complete it. Now, like the optimists among us will say that if we give the instruction followed by samples and then the query, then the model can actually figure out in what we are trying to say, and hence reason and then produce the output, or it's simply like looking at these instructions and few short, they are just like gibberish, but it can figure out that I need to fill the rest of the context. Let me as well fill similar to what was given earlier. Okay, so in this case, like we will actually in the later part of the talk, we'll talk more about reasoning. We want to teach the model to understand what it's doing and not just spit out. So in this case, if you don't do reasoning, if you don't use prompts like React or COT, then it's probably just doing like next token prediction. All right. Okay, so this is the goal. So we have given this prompt and we give it to the model, and it gives out the like whatever query that we want, right? So this makes it like a lot more easier to use. The developers don't have to worry about the syntax. Like kind of also like it's hard to execute this. It has to be executed on a GraphQL engine. So if you have a really good model to produce GraphQL, it becomes a lot easier for developers to use this in their apps. Now, so far we saw like this demo which we had at Ichkai was more about how can we generate the query. Now the other portion is like how do we even generate the schema. So although it looks more like a query, this is actually part of the schema. What this says is, if there is a request for any API location, then it has to be served from this endpoint, and there can be several such data which can be served in this API. One can be location, other can be a weather report, and there can be several other things. So I deliberately left out what is called as a type. Type would simply say, type would define what is location, whereas type query tells how to serve this location. So if you go back here, so this is the type, this is definition of people, and then here in this case, if you want to like kind of get data about bodybuilders, it says how to access that data. So likewise, so I have not shown the type here, but I'm only showing the query here. This is like how you fetch the data. Now, what we want to do is we want to run queries like this. So yeah, sorry for the GraphQL has this sort of a weird naming convention. So this type query is part of the schema. This is the query that you will see similar to SQL. So here I need weather for this particular, like say, I want like some location, and then I want to get like few columns. Like I'm not sure what clouds means, but beside maybe precipitation, I guess. So we want answers for this. The answer would eventually look like this, but right now there are lots of these endpoints. When we fire our natural language and then it converts into GraphQL query, how do we figure out which portion of this schema will answer this? And second, we also want, like say in this case, I'm asking for weather. I might give some city name. Then I need to convert the city name into an appropriate location and use that location ID to fetch the actual data from some other API, right? So we are calling this as a sequencing problem. So we need to know if we want weather, first we need the maybe some location, in this case mostly IP. We need to know the IP because like someone logs into a weather website from say Bangalore, they immediately know the IP from where the query comes in, and then they convert that into a location. Once you have the location, you can go fetch the report. So we are saying that although in this case it's trivial because there are only two APIs shown here, but you can imagine there are lots of other endpoints, and you have to choose in this order. First find the location, then go get the weather report. So this is what we are saying. Like say in this case location and weather report. If we can find this sequence, then we can kind of put this together in what is called as a sequence directive. So this comes like with the GraphQL engine. So as long as we are able to produce this order of endpoints, this kind of schema can be created. So the first problem that we try to solve is, can we find this ordering given some natural language. So I'll skip this. I'll go to this is work that I mean we have kind of created what is called as a GraphQL REST bench. So what we tried to do here was we took two data sets, Spotify and TMDB. These are like Spotify is a music data, whereas TMDB is about movies. The endpoints here are slightly different because the REST bench, which is a data set for function calling, so that was readily available. So we took that data set. But for like, I mean, if you kind of think about this, it doesn't matter whether we are generating GraphQL schema or GraphQL APIs or REST APIs or function APIs. So the idea is similar. So if you have lots of APIs, you need to select and order from a natural language. This kind of an approach will work. So we're saying like start with natural language, end with a sequence of APIs. So we ran some experiments on this data set, and what we are, I mean, because this is a sort of a resources paper, here we kind of try to show what is the performance of three models. Like all three are open source models, like Code Llama from Meta, DeepSeek Coder from DeepSeek, and Granite from IBM. All three models on two types of prompt styles. So again, we'll kind of talk a bit more, but these two prompt styles are somewhat very famous, like in the last couple of years. So COT stands for chain of thoughts. So basically, it kind of very intuitive. Like say instead of saying do this and then like say if you go back to the instructions here. So in this case, like you can simply give sort of like series of orders and say that your task is this and these are the examples, and then leave it at it. But it turns out a better way to say this would be, so this is the instruction, these are the examples, and you, before you give the answer, you give sort of an explanation why this answer is valid. So I need say this kind of query, this is the request from the user, and I know that these kind of tables exist or APIs exist, so I am putting this together. This is like sort of a very high level, like say explanation for why the query is created. So that's, I mean, we can think of this like more general forms of chain of thought. Like for example, like say I want like the BMI from a table. Then before you give the answer, you say that BMI is actually calculated with height and weight, and if we use this data, we have to collect height and weight, and hence I'm going to give this data. So sort of a chain of thought makes the model spit out why it's doing something. So we also give this in the examples, but we also expect the model to, instead of just giving the answer, give the reason why it's giving the answer, or it's like thought. What was the thinking behind that answer? So this COT was introduced like by Google like a couple of years ago in iClear 2023, and they, I mean, this kind of has been like a sort of a dominant style in the last couple of years. Now, React comes from a different perspective. Instead of asking the model to do everything in like say sort of a sequential manner, can we actually think of these as actions and observations? So first I give some, like maybe you split the problem into small parts. First you get some data, and then you tell the model this was the original ask, we solve some part of the problem, we call this as observation. Given this, what is the next action we should take? So the A here stands for action. So this is like a different style where the model, instead of in the COT, the model has to give some explanation or what was its thinking, whereas in React, it has to react to the observations that we are giving. So it will be inherently like more of a conversation. So these are the two prominent styles. We could have also included like say plain vanilla prompt, but we thought like this makes more sense. So we kind of published like, I mean, as you can see, like most of the models do much better on this task. Of course, like I mean, there were few other novelties that we introduced. Like if you use GraphQL schema for this task, the models do much better. So that was the like crux of this paper. All right. Again, like whatever we discuss now can be put into some sort of an agent, because if you're familiar with how agents are becoming more prevalent, so we also have an agent implementation. I will sort of skip that. All right. So this is some work. Actually, this is by Lakshmi in CSA here. She interned with me this summer, and we sort of took this problem and then tried to kind of make an improvement using reinforcement learning. The idea was like similar to like what we saw earlier. We do have some natural language utterance. We need to find a bunch of APIs to solve this, except that instead of us doing all the prompting or trying to kind of fine tune or teach the model, we will have an RL agent which kind of tries to identify where we are and go to the next state. So this is work still in progress. Like we have a sort of a extended abstract submitted, but the rest of the work Lakshmi is still working on. All right. Okay, so this is another paper that we presented at ICHKAI. This is an application of this work. So this is like much more applied. We were trying to use GraphQL for this problem of petition drafting. Say, for example, you go to a court and you want to file a petition. How do you fill details in a petition? Like say, some accident happened. I want to claim something from some company, insurance company or something. That's the case that you want to file. But how do you remember all the details? So can we fetch data for writing a petition, especially as a tool for advocates to use, or maybe even lay users? So we made some claims. So this, like Professor Bhatnagar and Professor Kumar, they are from the Delhi University like faculty. These are students that work with me. Sudipto, he's currently in IIT Delhi. He just started his PhD. All right. So, okay. So for just to take stock, we started with what is GraphQL. Then we saw that people have been starting to generate this GraphQL through language models. And then we saw we want to kind of create schema. Again, like why do you want to just make a data analyst or a data administrator create a schema? Can we create schema automatically? So that's what this has been like. We have like few papers in this and some ideas that we are working on. Now we will take a slightly kind of a different direction. What if we have to do all of this again on top of a database? So I mean, APIs are also, I mean, you can also query databases or lakehouse through APIs, but think more from a database point of view. Like if you have lots of these tables and you want to kind of create a schema with a subset of these tables, how do you create schema for this, right? So this is useful for what is called as a backend for front end kind of application. So someone wants to build apps on top of a lakehouse. So all I want to do is like say like a dashboard for kind of showing say some maybe like say the student details. So I only want to take some portion of the lakehouse, put them together, and then say that you can now ask any questions about students, academic details from this app. So how do I enable developers to fetch that kind of a data and automatically create a schema so that they are, I mean, as long as they know the requirement of their dashboard, they can create such dashboards. So there is no need for a data administrator or a data steward or analyst to create tables for them. They can automatically create, because like GraphQL eventually is going to go and get the data from the original lakehouse. So all we need is some schema which can be deployed, right? So there are like all kinds of personas involved. So the data steward persona is the one who would help create schemas. And then eventually you still want to query it. So in this case, in this example, we are showing that you start by asking the model to create a dashboard for handling customer complaints. Once you have created such a schema, then you can query like say I want like car transactions with this account detail. So this is the end user, whereas this is the person developing the app, right? So I mean, I know this is like slightly more application oriented, but this is again I'm motivating why we want to do any of this. So again, I won't go too much into this. Some of this is like work that we are still doing. There are lots of possibilities to achieve this goal. How do we generate GraphQL schema? I mean, like say if you're familiar with some of the latest ones, like say preference learning, that's like that could be one of the ways we can think of this, or we can think of this using like say what are called as like say Instruct Lab or GLAN is a Microsoft paper. These things involve sort of giving expert knowledge. So typically like you start giving models lots of examples and then they learn as much they can, but then they may not know the style. Like say what style means is like say in this case maybe like the model understands you have to get SQL or you have to generate GraphQL, but actually like how people write GraphQL, I mean what is the preferred way, how would a human write a GraphQL, that those kind of things are learned using preference learning. Whereas like this is sort of a laborious process. You give lots of examples, make the model learn the task, and then try to make the model learn preferences. So this takes a lot of effort. Like for example, ChatGPT, it was trained on like say pretty much the internet, and then they we believe that they used RLHF to understand how humans will ask questions and answer questions, and hence you have a system. Now, can we do this somewhat cheaply? So that's where these kind of systems come in, where instead of giving lots of data to train, can we give high quality examples given by experts? So there are a few methods which I've tried to give these experts samples. You still need to train the model with the samples, except that you get the samples from experts so that like the number of samples are less. You kind of this comes from the idea of curriculum learning. So you kind of try to pack in a lot of information in a few samples. So we are doing some work in this space. So I would kind of skip this and then go to like a more, I mean, so far we have talked about all the things that we have done. Now I will kind of make some observations. So this is generally like if you are interested in Lakehouse, where the industry is, right? So these are pretty much like the papers are as new as last week. All right. So like we have been so far talking about GraphQL generation. We can think of it's like very similar to SQL generation, the text to SQL task. So this bird dataset has been the dominant dataset in the last year. So the reason why I'm using this slide is the state of the art in this, like where we are stuck or where the industry is working on is on reasoning. So the idea here is if all the information to generate a SQL or GraphQL is present in the context, then we assume that the problem is solved. What is like till now not resolved is what if you need external knowledge, right? So someone like someone working as a data administrator or a data steward, they have some institutional knowledge which they may not write in the schema, right? Or you can think of this as like a lot of common sense, like people know a lot of things. I mean, the models don't know them. So how do we give that kind of a knowledge to them? So I'll just give a somewhat of convoluted example from the same bird is a data set. So what it says is someone is asking like say how many accounts are eligible for loans. Let's assume that this particular bank or say the loan giver has a rule that they give loans only to those customers who are owners or like say proprietors of a company. So this is an actual example in the bird data set. So if someone has to generate a query, if they simply say select count star from account where city equal to New York, they would be wrong, because there is a sort of this particular company has a convention that only those accounts which belong to owners are eligible for loans. It's very hard for any model to understand this. Like, I mean, where will you code this unless you specifically tell the model this is the rule in our bank? Maybe you give this as a knowledge graph and then ask the model to either fetch it or dump it in the prompt. Unless you give this knowledge, there is no way the model can learn. The model will faithfully do select count star from account where city equal to New York, because all of this information it can figure out from the query and the schema. This particular knowledge, which is very domain specific, that needs to be taught, or it has to be provided what is called as a system to kind of answer this kind of question. So that's why this is kind of getting challenging. So this bird dataset has these kind of questions which are sort of like non-trivial, whether it needs domain knowledge or it needs a numeric computation to be done there. It could, I mean, there is this whole idea of tool calling, but right now here it's more about just finding some computation, knowing synonyms. Like, how do you know F in a data set, which is very common? Like, we know pretty much, like all of us will know F stands for female, but the model may not know, right? We need to give this knowledge to the model. So, and finally, like say all these kind of things where the models typically do badly on these kind of constants or values that are added in the query. So these are kind of the harder problems in the BERD leaderboard. So BERD was a data set introduced for the text to SQL task. I mean, this has become sort of a holy grail for a lot of researchers. Even our IBM research kind of, we are in the, I mean, we used to be in the top position. Right now, the last month or so, 2-3 other teams have beaten us. So now we are in the 4th position. But on there are 2 metrics. One is like accuracy, another one is efficiency. On the efficiency, we are still in the 2nd place. So, I mean, like I'm just saying, like these are things happening in the last month. Like companies across the world, Alibaba, or there is one from Montreal, University of Montreal. All these teams are trying to do better on this BERD leaderboard, and these are all the harder queries in this dataset. Now, like say, carrying on from the thought from the last slide, so we kind of, why do models do badly on these data sets? So we can immediately see that we need external knowledge, but even if you provide some external knowledge in the prompt or using some RAG kind of system, the models don't do that well. So I mean, a BERD, they themselves give some kind of observation that we need some sort of a reasoning, multi-step reasoning, which is sort of lacking in current models. So if you can make the models to reason better, even beyond what is possible in COT, then maybe the models will do better. So of course, there is a lot of research on COT and other related ways to make models reason better. So that's kind of an open challenge. Now, few other examples of tasks which are harder. So we just saw, like say, external knowledge. We also saw a bit of numeric computation, but all this numeric reasoning is sort of hard. So, like, what do we mean by, like, say, a maximum power of a B? Like, how do we even know what is power? Like in this case, like say, there might be a column called horsepower. So how do we teach the model that when we say power, we mean horsepower? At least horsepower is sort of like somewhat semantically closer, but if it had some other column name, it would be harder. Then we need all sorts of like say common sense reasoning. I mean, this has been a problem in machine learning research for a while. Like say, how do we make models to understand common sense? So that similar problem exists in this task as well. And then few other, like say some hypothetical, like, I mean, this is like more closer to the previous example we saw about getting a loan. So these are some of the problems. So this data set, which was released after BERD, so they claim that this is much harder than even the BERD data set. So they claim that a lot of these models do much poorly on this data set. So maybe like the next like if people are interested, they might want to. They also have a leaderboard, so people try to submit solutions. So they have released a new data set, which they say is more realistic because it comes from a data warehouse. So like there could be a person here who wants to kind of find the actual physical space to create an office. So that level of like say practical utility. So they say that they have released a data set, and they also report that a lot of these models don't do well if, I mean, if it's probably easy to find, like say university salaries, these kind of data language models have kind of sort of mugged up. But if you give totally like new or more practical data sets, they don't do well. So this is like a new data set or a benchmark for text to SQL. Yeah, I mean, a typical query that we have to generate will look like this. So because it's a benchmark, they provide the gold result. And here they are using, like say, ChatGPT, GPT-4o, and they're showing the results. And they also point out like there are a lot of things the models don't get right. So yeah, this is like last week. Okay, so now these are the problems that we saw. How do we solve this? Like one approach is like if the problem in all these data sets is models need more knowledge, can we brute force give a lot of knowledge? Turns out yes and no. Like people have been infusing knowledge into models for a while. So this is actually Kinshuk. He's currently in CDS under Professor Danish Pruthi. He's doing a PhD. So he was with the like he worked with me when he was in Delhi University. We tried to infuse simple knowledge graph knowledge into all these kind of models on a relatively easy task of relation prediction. So finding out president of US, say Barack Obama or whatever at that time, that is a relation prediction task. And we tried to sort of give a lot of knowledge from say triples to this model, and then we evaluated it. So this again is a has been an ongoing research. Like Flantify models are from Google. So they have been using sort of a brute force approach. Like say you train with lots and lots of data. Wikidata is a knowledge graph which has like say millions of about 45 million triples. So they infused 15 million of them and then they got some result. What we wanted to show here was maybe we don't have to do that. We don't have to infuse with millions of triples. Instead, you few examples in the context, in the prompt, then also we can do like even if you simply have a sentence about this person. For example, in this particular say Obama's like say aunt, it's very unlikely that Obama's aunt is present in a knowledge graph. Like say or in this case like Michelle Obama's aunt. But there could always be a news article or some sentence about this person. So what we argued in this paper was if we even if you don't have triples, if you simply give a sentence that can be easily fetched from the internet or from a say your like you have an index of sentences, if you give this, the models do better. So we got some results. So this was like it got published in Icon in 23. So this is like maybe this kind of a solution where you provide knowledge directly into the model and then hope the model does better. That could be one approach. People are still trying it. But people are increasingly doing more things now, which is around reasoning. So, I mean, if you're familiar with, like, say, planning, which is like if you have to generate, say, a schema or a query, or even to generate, like, say, a long paragraph or a document, you probably want to plan. So it's a well-known thing that, or people have been arguing that large language models cannot plan. They don't do reasoning that well. They need knowledge given to it in some cases from an external source. And they also need things like prompt assistant or an assessor to verify. So these are all the things that are needed. So people have been coming up with a lot of ways in which how all these things can interact together. So we also have a paper which again we presented in HKI. So we are calling it as the Sherpas framework. Sherpas for, like, say, Sherpas take mountaineers to the top of the mountain. These are Sherpas which are supposed to help the model do better. So we came up with this, and we kind of this is a more of a opinion or a vision paper. So we are saying that we will have a lot of these agents, and each of these will be autonomous, and they will work with the output of a large language model in order to do a particular task. It could be text to SQL or GraphQL generation better. And what particular thing the model lacks, is it knowledge or reasoning or planning? Those kind of things we have to figure out autonomously. So that's what this, we are calling it as the Sherpas framework. So this was like, I mean, a lot of things that we are doing now try to implement this framework. So we have some ongoing work which are not yet published, but the framework itself, we kind of, it's available on archive as well. All right, so just to summarize again, like we did in the first portion, in the second half of this talk, we wanted to see some open problems in querying a lakehouse. The predominant problem seems to be about reasoning. Models are not reasoning that well. We know that they have very little planning capabilities. And how do we solve? Like, there are a couple of approaches that our team has tried. One is knowledge infusion. The other one is using agents, which do a lot of these things. All right, so I'm kind of done with what I had. So if people have comments or questions, feel free to ask. All right, thanks.
Thank you, Balaji, for
Cool.
the talk. Thank you.
All right. Sure, yeah.